Okay, I'm going to start this video by going to a previous problem that I had solved, and right here, cos inverse of -1/2. I have no idea how I got this strange angle, but it's clearly not 133.3. Somebody pointed that out to me. Thank you very much. The answer here is actually 120 degrees. So I'll change that there, and there, and there. Obviously, this is not going to show up in the previous video. It's going to show up in this one. Good, so that's the correction. All right, now I'm going to go to the section that I want to get started with in this video. And as you'll notice from the heading, it says miscellaneous trig problems and solutions. And then you have a nice worksheet. I know it says trig worksheet, but it's trig worksheet, the long promised trig worksheet together with other problems. 25. So without further ado, let's get started. First problem says, solve the equation sine of x minus 30 is equal to cos 4x. And you're solving that for the domain x between 0 and 180. Okay. Now, if you look at that equation, it's a bit complex. You look on the left-hand side, you have the sine function, and it's the sine of a compound angle. You look on the right-hand side, and it's the cos ratio, the cos function. And it's the cos of a quadruple angle. Not so easy to handle. However, one good way to do this problem is to try to get the same trig ratio on both sides. Either the sine trig ratio on both sides or the cos trig ratio on both sides. What I'm going to do in this first pass of the problem, I'm going to have the cos trig ratio on both sides. So I'm going to change the sine function into the cos function. So here I have written, we would like to take the sine function and rewrite it as an equivalent expression in terms of the cos theta function. And how do we do that? Well, I'm going to show you, let's utilize our knowledge of transformations. If you look at the graphs that I have drawn there, the cos function, if I take the cos function and shift it or translate it by 90 degrees to the right, I'm going to end up with the sine function, right? So from the diagram, to get the sine function, we translate the cos function by 90 degrees to the right. So it's written there. Give me a minute. Let me redo this part. Yes. So the sine theta expression is formed by taking cos theta and by taking cos of theta minus 90. Remember the translation or the transformation, g of x is equal to f of x minus a when you translate to the right. You could also check this, by the way, by looking at, by opening this up and checking the compound angle identity. This thing right here, cos of theta minus 90, that will be cos theta, cos 90, plus sine theta, sine 90. Cos 90 is 0, sine 90 is 1. This part goes to 0, this part goes to just sine theta times 1, which is sine theta. So indeed, cos of theta minus 90 is sine theta. All right. Get rid of that. I don't really want that. That's just a side proof as such. Good. So I want to take the sine function in this case, which is sine of x minus 30. Sine of x minus 30, that's my theta in this case, and we write it as cos of the same x minus 30 minus 90, which is cos of x minus 120. So the original equation, which was written as sine of x minus 30 is equal to cos of 4x, to be solved for x between 0 and 180 inclusive. We're going to rewrite the left-hand side. Instead of writing it as sine of x minus 30, we rewrite that as cos of x minus 120. We'll rewrite the right-hand side the same way it is, cos of 4x. And now we're going to solve that as equivalent for x between 0 and 180 degrees inclusive. Okay, now what's the benefit of doing what I just did? What's the benefit of converting the sine function into the cos function? Well, because I have cos on both sides, and now I have options. I can throw both trig expressions in one side and use factor formulae, where I convert a sum or difference into a product. Or I can use directly from right here, I can use the general solution technique. Cos A equal cos B. So here, I'm going to start with the general solution technique. Here's why this is so cool. I'm going to just cos inverse the other side. So I'll get x minus 120 is equal to cos inverse of cos of 4x. Everybody knows that cos and cos inverse will disappear. So this just ends up being 4x, which is P, my principal angle. Remember that? From the general solution technique, just look back at the previous video. That's going to give you some heads up on that. Now, when it's the cos function, this is like your alpha. We usually call that alpha. And this is your P, your principal angle. And the general solution for the cos function is alpha is equal to 360n plus or minus P. I think, is it? Double check. Yes, 360n plus or minus P. Therefore, my alpha in this case is the x minus 120, and that's equal to 360n. Oops, let me write the proper n. 360n plus and minus, and P in this case is 4x. This is going to split into two separate equations. This is going to split into either x minus 120 is equal to 360n plus 4x, or x minus 120 is equal to 360n minus 4x. My job is to find x. X is the variable that I'm solving for. In this case, let me see, if I throw over the x on the right and bring over the 360n, I'll get minus 360n minus 120 is equal to 3x. I can factor out a minus 120. Minus 120 comes out. What's left inside? 12 threes. This looks like 3n plus 1 is equal to 3x, from which I can get x is equal to 120 over 3, that's 4. Minus 120 over 3 is minus 40 into 3n plus 1. This is part of my general solution. The other part of the general solution will come from this guy. I'll bring over the minus 4x. I'll get 5x on this side is equal to 360n plus 120. 5x is equal to, I can factor the 120 from this as well. 120 into 3n plus 1. And if I divide by 5, I get x is equal to 5 into 120. What is that? 120 over 5. That 24? Yes. So that would be 24 into 3n plus 1. So if I wanted the general solution, the question didn't ask me for the general solution directly, but I can find my set of values of x from the general solution. But I'm going to summarize the general solution here. General solution is minus 40 into 3n plus 1, as well as 24 into 3n plus 1, where n is a member of the set of integers. By the way, that's the actual symbol, meaning positive, negative, and 0. There. Now, let me see if I can find a solution within the given domain. So let me go back again, write back the original equation. The original equation was, what's the original equation? Sine of x minus 30 is cos 4x. Sine of x minus 30 is cos 4x. And I wanted to solve that for x between 0 and 180. Okay, no problem. If you look at the first one, you clearly can't put positive values of n, positive values or 0 for n into the first one because you're going to get negative angles. I want only positive angles between 0 and 180. So I want to start off my first negative value of n. I'm going to plug into this one. This is x is equal to that, by the way. So x is equal to minus 40 into 3n plus 1. When n is minus 1, x is minus 40 into, that's minus 3 plus 1, which is minus 2, times minus 40, that will be 80. When n is minus 2, x will be equal to minus 40 into minus 6 plus 1, that's minus 5. This gives me 200. So that's clearly not a value. That's gone outside of the domain that I'm looking for. And I'm going to take the other half, which is x is equal to 24 into 3n plus 1. When n, and I can put in 0. Yes, I can start at 0. When n is 0, x would be 24 times 0 plus 1, which is 24 degrees. When n is 1, x would be 24 into 3 plus 1. 3 plus 1 is 4. 24 by 4, I think that's 96. When n is 2, x is equal to 24 into 6, 2, 3, 6, and 1, 7. Hope I didn't go outside the range here. 7 by 24 is 168. Barely made it. And I'm sure if I try n equal 3, 3 is 9 and 1 10, that would be 240. Too big. So my solution set within the given domain would be x is equal to, starting from the smallest, 24 degrees, 80 degrees, 96 degrees, and 168 degrees. And any one of those angles, you can check it back in the original equation. Pick any one of the solutions. Pick any number and plug it back. Let me try it. I'll pick 80. I'll pick 80. So on the left hand side, it's sine of 80 minus 30, which is 50. Sine 50. Sine of 50. That is minus point. Why is that a negative number? Nonsense. Sine of 50 equals. Something's wrong with my calculator. It's in radians. Mercy. Degree radian. I give up. Try this. Sine of 50 could never be a negative angle. 0.766. 0.766. And on the other side, it'll be 4 by 80. 84 is sine of 4 times 80 equal. This thing is making a not sine, that should be cos. Cos of 4 times 80. 0.766. Great. Good. And you can try any of the other angles and show that the two sides of the original equation will balance with any of those angles. So that's one technique we could have used. A second technique we could have used, I'm going to solve it another way as well, showing the flexibility of this trigonometry. A second method we could have used, we could have taken it from the point where come on, where did I change it over? Cos, where I changed the sine of x minus 30 to cos of x minus 120, right? Sine of x minus 30 is cos of 4x. I'm going to change it over to cos of x minus 120 is cos of 4x. From there, this is method 2. From right there. And what we're going to do, we're going to throw them both in the same side. So I'm going to throw what's in the left over to the right. So this equation becomes cos of 4x minus cos of x minus 120 is equal to 0. And if you look at that, it's not in the form cos p minus cos q is equal to 0. And what's the identity for cos p minus cos q again? Cos p minus cos q. Don't remember, so I gotta look it up. It's back here somewhere. I derived it all before. Let's see. Right there. Cos p minus cos q minus 2 sine half the sum, sine half the difference. Is equal to minus 2 times sine of p plus q over 2 sine p minus q over 2. So I'm going to rewrite cos of 4x minus cos of x minus 120 as minus 2 sine. You add them together, 4x plus x minus 120. That's 5x minus 120 over 2. And then sine of half the difference. 4x, let's see, 4x, and you subtract x minus 120 over 2. That gives 4x minus x, that's 3x plus 120. 3x plus 120 upon 2, like so. Okay. So, because cos 4x minus cos of x minus 120 is equal to 0, it obviously means that it's equivalent minus 2 sine of 5x minus 120 over 2 times the sine of 3x plus 120 over 2 must be equal to 0. And because I have a product equal to 0, then that means each part of the product would be equal to 0. So therefore I can either say sine of 5x minus 120 upon 2 is 0, or sine of 3x plus 120 upon 2 is equal to 0. Great. And right here, these at this point, this doesn't lend itself so easily to using the cast diagram technique. So we're going to jump straight back into the general solution technique again. So let's go. 5x minus 120 upon 2 is equal to sine inverse of 0, which is 0, which is my principal angle. My principal angle is 0. This is my alpha, and this is my principal angle. You remember when we deal with the sine function, then the general solution is alpha is equal to, 180 n plus minus 1 to the n times p. Lucky for us, p is 0, so alpha, which is 5x minus 120 upon 2, is equal to 180 n, and that part goes to 0, right? If I substitute p equals 0 there, then that part goes to 0. So I'm going to solve this for x. 5x minus 120 is equal to 360n. Throw over the 120. 5x is equal to 360n plus 120. I'm going to factor out the 120 and at the same time divide it by 5. And I'll get x. X is equal to 120 into 3n plus 1 upon 5. If I tidy that up, that would look like x is equal to 5 into 125. Is it 24? 120 upon 5. Yes, it's 24. So that would be 24 into 3n plus 1. That looks kind of familiar. And then take the other half. I'll do the general solution on this as well. 3x plus 120 upon 2 is equal to sine inverse of 0, which is 0, which is my principal angle. This is my alpha. This is my principal angle. General solution is alpha is equal to 1a to n plus minus 1 to the n times p. P happens to be 0. Alpha in this case happens to be 3x plus 120 upon 2. And that must be equal to 1a to n plus 0. The p is 0. 3x plus 120 is equal to 360n. 3x is equal to 360n minus 120. X is equal to 120 into 3n minus 1 upon 3. Or x is equal to 3 into 120. Oops. Did I mess something up? Whoa. I really don't want to learn more at this point, you know. Okay, where was I? Before I was so rudely interrupted. Yes. Am I missing something here? I'm missing a minus sign. 3x plus 120 over 2. X is 40 into 3n minus 1. No, X is, let's see, what do we have here? I don't think I'm missing anything. Yes, from here, X would be, there's 120 rather, into 3n minus 1 upon 3. And 3, that's 40. X is equal to 40 into 3n minus 1. Now, this is the general solution if you use this technique. Let's see. X is equal to 24 into 3n plus 1 and 40 into 3n minus 1, where n is a member of the set of integers. And I have a feeling, depending upon the value of n that you plug in, that will give you the same solution set. So let's see. Into the first one, I'll start with n equals 0. So x is equal to 24 into 3n plus 1. When n is 0, x is 24 into 0 plus 1, which is 24 degrees. When n is 1, x would be equal to 24 into 3 1 is 3 plus 1 is 4. That's 96 degrees. When n is 2, x is equal to 24 into 326 plus 1 is 7. 24 by 7. I think that's with 168. Double check. Yes, 168 degrees. And if I try n equal 3, that would go past. For the other half, x is equal to 40 into 3n minus 1. When n is, let me see, if I try n equals 0, I'll get a negative angle, so n equal 1. When n is equal to 1, x would be equal to 40 into 3 minus 1. That's 80 degrees. If I try n equal 2, I think that will go past 6, 5. Yes, that definitely will go past. So I get the same solution set. Right? Same solution set. Right? And if I lay it out from smallest to largest, x is equal to 24 degrees. 24 degrees. 80 degrees. 96 degrees. And 168 degrees. So we have two methods of solving that problem. Good. Here is the first homework problem I have for you. Notice how we change both sides of the expression to cos. Well, I want you to show your flexibility and convert both sides of the equation to sine, and then use both methods to solve. So, in other words, you're going to take cos theta and convert it to sine of theta plus 90. All right, let me show you what I mean. Let's go back up here. To get the cos theta function, I have to start with the sine theta function and slide it 90 degrees to the left. Sliding it 90 degrees to the left means I add 90. So, cos of theta is sine of theta plus 90. So the right-hand side of the original equation, which was cos of 4x, can now be written as sine of 4x plus 90. So now both sides of the original equation would look like, I keep forgetting. The original equation was sine of x minus 30 is cos 4x. Sine of x minus 30 is cos 4x. You're going to keep the left-hand side the same, sine of x minus 30. But the cos 4x will be written as sine of 4x plus 90. And then you'll apply both techniques, the general solution technique up front, and then bring both expressions on the same side, so you'll get sine p minus sine q. Solve it the same way. In both cases, again, you should get the same solution set. Show your versatility with the use of all that stuff you learned in the trigonometry. All right, I'm going to end this here. So at least you know what you're shooting for. The same set, same solution set that we got before. Excuse me, some water. The next problem is a proof, and there are actually two ways it can be done. I'm going to do it one way, and then I'll point out the other way it can be done. You'll try it that way. Prove that cos theta plus cos beta all squared plus sine theta plus sine beta all squared is equivalent to 4 cos squared of theta minus beta over 2. Well, the first thing, if you look at that, the first thing you might want to do is to start opening up the brackets. That's not a bad way to do it, but maybe it's not the most efficient way to do it. But that's the way I'm going to do it anyway. I'm going to open up the brackets. I'll give you the more efficient way to do it. I'll point it out, and then you'll do it that way. So let's see what happens. We're going to take the left-hand side and start opening up the brackets. Cos theta plus cos beta, all squared, becomes cos squared theta plus 2 cos theta cos beta plus cos squared beta. Open up the next bracket, we'll get sine squared theta plus 2 sine theta sine beta plus sine squared beta. And you're already seeing certain expressions like cos squared theta and sine squared theta and cos squared beta and sine squared beta. We'll put them next to each other. Cos squared theta plus sine squared theta plus cos squared beta plus sine squared beta. And then the other parts we put next to each other as well. 2 cos theta cos beta plus 2 sine theta sine beta. Everybody knows this is 1. Everybody knows that's 1. So that's 1 plus 1 plus, and then this is 2 into cos theta cos beta plus sine theta sine beta. This is 2 plus 2 into and that part in the brackets looks like the expanded form of cos of theta minus beta. Cos of theta minus beta. Now if you look at the result that they have, the angle is theta minus beta over 2, which is half of the theta minus beta that I have there. So what I'm going to do, I'm going to rewrite this as follows. I'm going to rewrite it as 2 plus 2 into, and then the cos of theta minus beta, I'll write it as cos of 2 times theta minus beta upon 2. All I did was to multiply by 2 and then divide back by 2. I didn't change anything. But the reason for doing that is so that I make it look like a double angle, cos 2 of some angle, where this some angle is theta minus beta over 2. And everybody knows that cos 2x, you can rewrite that. There are several ways to write that. The end result looks like they want the cos squared function involved, right? So we're gonna rewrite. We're gonna rewrite cos 2 of theta minus beta upon 2 as 2 cos squared of the angle minus 1. This is the part in the brackets, right? Cos 2x is 2 cos squared x minus 1. I still have a 2 outside the bracket and then a plus 2 here. Okay? This is equal to 2 plus, open up the bracket, we'll get 2 2's, 4 cos squared of theta minus beta upon 2. And 2 by minus 1 is minus 2. These two cancel out. What's left over? The result is 4 cos squared of theta minus beta upon 2. Hence proven. QED. There. The other method, I'm going to leave that for you to do. Show some versatility again with this trigonometry. Here's what you're going to do. On the left-hand side, you're going to use the factor formula there, and then the factor formula there. So in the first bracket, you'll use cos P plus cos Q. Well, in this case, it's cos theta plus cos beta. The factor formula for that. And in the other one, you'll use sine theta plus sine beta. Use the factor formula in each case and then see what shakes out from that. Okay. That's enough for that one. Here's another proof that they're asking us about. Let's see how good we are. By the way, some of these, if you want to stop the video and try it on your own first, then that's up to you. But I'm just working out. There are many more to follow. Many, many more that you'll have to do on your own. But, you know, good practice too. All right, they're asking us to take 1 minus cos theta into 1 plus sec, 1 minus cos A into 1 plus sec A, and show that it's the product of sine A times tan A. Wow. Well, let's see. The first thing I would think of is to open up the brackets. So that would be 1 plus sec A minus cos A minus cos A times sec A. Okay, this is 1 plus sec is 1 upon cos. Everybody knows that. Minus cos A. And then minus cos A times 1 upon sec is 1 upon cos. These two will cancel. What do I have left? 1 plus 1 upon cos A minus cos A minus 1. The 1s will cancel out. And I have left 1 upon cos A minus cos A. If I form an LCM here, this becomes 1 minus cos squared A upon cos A. In my numerator, 1 minus cos squared, we should know we can rewrite that as sine squared. Sine squared A upon cos A. Sine squared can be written as sine times sine. So that's sine A times sine A upon cos A, which would be rearranged to look like sine A upon cos A times sine A. And this portion here is tan, and that portion is sine. Hence, tan A sine A. So I'll just write it back in the order that they want it, which is sine A times tan A. Hence proven. Not too bad. What's the next problem? Not ready for that one yet. Yes. Another proof. Prove that 1 minus cos 2a plus sine 2a upon 1 plus cos 2a plus sine 2a all can be simplified just to give tan A. Now let's try this. The first thing I'm thinking of is to get rid of all those double angle identities. So sine 2a, there's only one expression you can use for that. Cos 2a, you have multiple that you can choose from. The one I'm going to choose is, well, I get it. I'll choose the one in which the 1 will cancel out with the 1 on the outside. So here's what I mean. I'll take the left-hand side, which is, I'll write it back first. 1 minus cos 2a plus sine 2a all upon 1 plus cos 2a plus sine 2a. I'll write it as 1 minus into. Now cos 2a can be written as 2 cos squared a minus 1 or 1 minus 2 cos squared a. I prefer to use that one because as you can see, when you push the minus inside, the 1 on the outside minus the 1, the 1s will cancel out. That's my only reason for using 1 minus 2 cos squared a there. And then sine 2a is 2 sine a cos a. On the bottom, 1 plus, I will use the other one, which is 2 cos 2. Sorry, this should have been 1 minus 2 sine squared a, right? Messed that up. I don't know my identities. This should be 1 minus 2 sine squared a. Yes. And on the bottom, I can use 2 cos squared a minus 1. There, like that. Of course, for sine 2a, I still have only one thing I can use, which is 2 sine A times cos A. Let's see if you can simplify a little further. In the numerator, the 1 minus 1 will disappear. The 1 that goes into the bracket will make that first part positive 2 sine squared A plus 2 sine A cos A. On the bottom, the 1 and the minus 1 will disappear, and I have 2 cos squared A plus 2 sine A cos A. What's common in both numerator and the denominator? Well, let's see. 2 is common, and sine A is common. If I factor 2 and a sine A, what's left? Sine A plus cos A. On the bottom, 2 and cos A is common. What's left inside? Cos A plus sine A. These two are the same, so they cancel out. The 2's will also cancel out. What's left over? Sine A over cos A, which is tan A, and it's proven. That's not too bad either. Okay, I have another problem. This one is, these are very popular. In the last several years, they pretty much always give you something looking like this to solve. So we're going to pay a little more attention to this one. Well, we always pay a lot of attention to all our problems, right? All right. So the first part says they want you to re-express 3 sine 2 theta minus 2 cos 2 theta in the form r sine of 2 theta minus alpha. Okay, that should not be difficult. We've done this before. And if we've done it before, we can do it again. There. Let me open up some space at the bottom as well. So we'll start by saying let 3 sine 2 theta minus 2 cos 2 theta be equivalent to r sine of 2 theta minus alpha. If we expand the left-hand side, sorry, the right-hand side, we'll get 3 sine 2 theta minus 2 cos 2 theta is equal to r into, I'm going to use the compound angle identity on the right. This would be sine 2 theta cos alpha minus cos 2 theta sine alpha. 3 sine 2 theta minus 2 cos 2 theta is equal to, we're going to put the, by the way, in these expressions, r is always greater than 0, and alpha is always between 0 and 90. So, right, let's continue. R and alpha are constants that we're going to find. So we're going to put the constant parts together. This becomes r cos alpha all times sine 2 theta minus r sine alpha times cos 2 theta. And then we'll equate the coefficient of sine 2 theta and cos 2 theta. The coefficient of sine 2 theta on the left is 3. Coefficient of sine 2 theta on the right is r cos alpha. Equate them and you get r cos alpha is equal to 3. Coefficient of cos 2 theta on the left is minus 2, and on the right is minus r sine alpha. If we throw away the minuses on both sides, we'll just get r sine alpha is equal to 2. And now I have two equations and two unknowns to solve. If I divide them, I'll get tan alpha is equal to 2/3. Alpha is equal to tan inverse of 2/3, and I hope I can find this. Tan inverse of 2 divided by 3 equal 33.7 degrees. Alpha is equal to 33.7 degrees. R can be usually found from the square root of a squared plus b squared, which is the square root of 2 squared plus 3 squared. 9 and 4, 13. Square root of 13. I'll leave it as a third value for now. Okay. Now what? Now I simply plug that information back up here. So I've answered the first part. 3 sine 2 theta minus 2 cos 2 theta is written as r root 13 times the sine of 2 theta minus alpha, and alpha is 33.7 degrees. Voila. That's our first part. The second part is asking us to solve a certain equation. You can't draw a straight line, buddy. Still can't draw a straight line. Anyway. Yes, the second part is asking, hence, solve the equation. 3 sine 2 theta minus 2 cos 2 theta equal root 13 upon 2 for theta in the range 0 to 360. Well, we just found an expression for an equivalent expression for 3 sine 2 theta minus 2 cos 2 theta. And that equivalent expression is root 13 times the sine of 2 theta minus 33.7. What we're going to do, we're going to put that instead equal to root 13 over 2. The root 13s will go, and I end up with sine of 2 theta minus 33.7 degrees is equal to a half. So now I'm solving that for theta between 0 and 360. Now, again, it's a little more tedious to try to do this using the cast diagram technique. Notice how I've strategically moved over to the general solution technique most of the time. Most of the problems I have, I use the general solution technique and then plug in values of n into the general solution to find a solution within a specific range. Works pretty well. So I'm going to use the general solution technique here again. Let's see. You remember how that goes? 2 theta minus 33.7 is equal to sine inverse of a half, which is, I know that's 30 degrees. I don't have to look that up. And that's my principal angle. This is my alpha. This is my principal angle P. General solution technique says to find alpha. Actually write that. General solution says alpha must be equal to 1a to n plus minus 1 to the n times p. Alpha in this case is 2 theta minus 33.7, and that's equal to 1a to n plus minus 1 to the n times 30. It'll be a tad more complicated. And theta is equal to 1a to n plus minus 1 to the n times 30 plus 33.7, and divide that by 2. I will get all of my solutions from this guy. This is a general solution where n is a member of a set of integers, all integers, positive, negative integers, and 0. Okay, what are we going to start with? N equals 0. Is this plus 33.7? Yes. N equals 0 when, come on. When n is equal to 0, theta will be equal to, that goes to 0, that part, minus 1 to the 0. Minus 1 to the 0 is, anything to the 0 is 1. 1 by 30 is 30. 30 plus 33.7 over 2. That is 31.9. Okay, that's my first solution. N equal 1. I will get theta is equal to 180. Minus 1 to the 1 is minus 1. So that's minus 30 plus 33.7 all upon 2. Divide that by 2. 91.9. N equal 2. Yeah, I can double check these answers again, because I can't add, right? There's subtract or multiply or divide. Theta is equal to 180 by 2, which is 360. And then, what do I have here? Minus 1 squared, that's a positive 1, so this is plus 30, and then plus 33.7 divided by 2. That's 211.9. I don't know if I have any more. Maybe I have one more. N equal 3. Let's see. Theta would be equal to 180 by 3. 540. Okay. Minus 1 to the cube, that's minus 1, so that's a minus 30. Still plus 33.7. Divide that by 2. That's 3.7. Divide that by 2, and that gives me 271.9. And I don't think I have another one. 4, let me see, 4 by 180. That'd be 720. And 4, I'd be adding 30 and adding 33.7, dividing by 2. That would go over 360. Definitely. Yes. So these are my 4 solutions within the range. I don't think a negative value of n would do it. No negative value. So those are my 4 solutions for that equation within the given range. Solution set. Theta is equal to 31.9 degrees, 91.9 degrees, 211.9 degrees, and 271.9 degrees. I'll check one. You know, I'm prone to making errors, so let me check one back into the original equation and see what happens. The original equation was 3 sine 2 theta, 3 sine 2 theta minus 2 cos 2 theta is equal to root 13 upon 2. And I'll plug in, I'll take the 211.9. 3 times the sine of 2 times. Let's see what that will give me. How quickly can I do this? 3 times the sine cos. So this is 1.808, and 13 upon 2 is equal to 1.802. So that's good enough for me, because remember, you're plugging in an approximate value for the angle. Close enough. Good. So that's a good check. That's my solution set. Now the next part of this same problem, all these parts are very prominent. They love to give these. So let's see how we're going to handle this last part. We have a function that says you're given that some function of theta, f of theta is equal to 1 all upon 8 plus 3 sine 2 theta minus 2 cos 2 theta. Find the maximum and minimum values for f of theta and the smallest positive value of theta for which this occurs. Maximum and minimum. You look at f of theta, you see the numerator is a constant. So obviously, if you want to maximize that expression, you need to minimum. First of all, before I say any of that, let me rewrite f of theta. F of theta will first be rewritten as 1 upon 8 plus, and the 3 sine 2 theta minus 2 cos 2 theta, we'll rewrite that. We will rewrite that as, remember, that was written as root 13 times the sine of 2 theta, and I don't remember the angle, 2 theta minus 33.7. All right, now I'll give my explanation based on the way the function looks now. The numerator is a constant. For me to minimize the entire function, I will have to maximize the denominator. And the denominator is maximum, so f of theta is minimum when the denominator is maximum. That is when sine of 2 theta minus 33.7 when that's equal to 1. Okay, so let's put that entire part equal to 1, and minimum value for f of theta would be 1 over 8 plus root 13 times 1, which is 1 over 8 plus root 13. Y'all know about surds and all that fancy stuff, right? This is 8 minus root 13 on top, and on the bottom, it'll be 8 plus root 13 times 8 minus root 13. All right, working that. This is 8 minus root 13 all upon 64 minus 13. 54, 55. Oops, what? Yeah, 51. So this is 8 minus root 13 over 51. That is the minimum value of f of theta. The decimal equivalent would be what? 0.086. 0.0862. All right, so you got it in surds as well as a decimal to 3 significant figures. Now, what's the minimum value of theta that causes this to happen? Give me a minute here. Now you gotta start writing more left justified. There. Yes. What's the smallest positive angle that would make that happen? Well, remember, first of all, we took sine 2 theta minus 33.7. And we had to put that equal to 1. Now, sometimes it's not very obvious what the smallest positive value is. So my suggestion is run the general solution technique on this and find the smallest possible value. So that's very simple to do at this point because we've been doing it so often. 2 theta minus 33.7 is equal to sine inverse of 1, which is 90 degrees, which is my principal angle P. Alpha, which is 2 theta minus 33.7, is equal to 1/8 to n plus minus 1 minus 1 to the power n times P. 2 theta is equal to 1/8 to n plus minus 1 to the n times 90. That would be plus 33.7. And I'll just make this theta one time. Theta here, so therefore you divide that by 2. The smallest value of the smallest positive angle occurs, let's see, if I make n, first of all, if I make n a negative, that entire angle would be negative. If I make n 0, then that would give me the smallest positive angle. Any other value of n, 1 and so on will give me larger values. Yes, so when n is 0, theta is equal to 1/8 times 0 plus minus 1 to the 0 times 90 plus 33.7 all upon 2. Theta is equal to minus 1 to the 0 is 1, so that's just 90 plus 33.7 upon 2. 61.9 degrees would be the smallest positive angle. So if I were to summarize that, minimum value of f of theta is 8 minus root 13 upon 51, or 0.0862. And that occurs when theta is equal to 61.9 degrees. There are other values of theta that will give you that minimum value, but this 61.9 is the smallest positive value of theta that would make that happen. I'm going to leave the other half for you to do, because remember, this part was you have to find both the minimum and the maximum. I did the minimum one. F of theta would be, I'll set it up and then you will run with it. F of theta is maximum when the denominator is minimum. Remember, the smaller the denominator, the larger the fraction if the numerator is a constant. And the numerator is minimum when the sine of, that is, when the sine of 2 theta minus 33.7? When that's equal to minus 1. So if this is maximum, when that part, because you'll have to be subtracting root 13 from the 8 this time. All right, so you're going to finish this up. You're going to plug sine of 2 theta minus 33.7 into f of, as minus 1 into f of theta. Find the expression, and then set up the general solution technique, just like I did. And finish up and solve for theta, the smallest positive value of theta, for which that's going to happen. And I'm going to end this video right here. All right, now you have a rather lengthy worksheet. This is probably the longest worksheet I've given you. I hope you're happy. You kept asking me about the trig worksheet. Here it is. Here are the first 4 problems. It's lengthy, so I gotta show you. You could screenshot or whatever. Here are the first 4. And then this is another one with an envelope. I can only show you the diagram and maybe a part. This is number 5. Here's the diagram. Yeah, that's the diagram. And then the rest of the problem, what's being asked, up to, where's the end of the problem? There. That's number 5 on its own. Nice problem. Then a whole bunch from number 6. Let's say I think I did number 6. Yeah, the ones I circled in red are the ones I picked out at random and did. Not because they were easy. I just picked them at random. You better believe me. All right, from number 6 to, let's say, number 12 there. And then number 13, 14, 15. Number 13 is a proof. 14 and 15 has more to do with everything in Module 2 than just trigonometry. If you notice, it says here the 2 Module 2 tests or exams from the textbook, that Dipchand textbook that we're using. There are 2 Module 2 tests in there. You're going to go through both of them, page 338 and 339. This would give you a good workout on all the topics that we've covered in Module 2. Trigonometry. By the way, this video here concludes everything I wanted to do in trigonometry, everything I have to do on trigonometry. Vector analysis. I did quite a bit of work on that. Coordinate geometry, quite a bit of work on that. Parametric equations, quite a bit of work on that, low key. All of these. Those two module exams going to give you a good workout in that, yeah. So I don't necessarily work them on the exam conditions. If you want to, that's up to you. You can time yourself, but that's a requirement. And I'm going to end this video right here because the next set of stuff I have to come back with is going to go back to calculus. I have to do a little bit of work. I have a little bit of work left on differentiation from first principles and limits and continuity. That will end differentiation. And then I think I have a bit of work left on integration, but integration is not that lengthy for the Unit 1 syllabus. So, and I think that's it. That would be it for the entire syllabus. All right, so a couple more videos, and then we're good. All right.